What's going on, smart people? I'm sorry in advance if I sound like a dying washcloth today. I'm getting a little sick, so you have to bear with me on that. But I got my final homework assignment of math methods of the entire, I guess for the rest of my life. I'm not sure that I'll ever take another math methods course again. But I got my final math methods homework, and it is on tensors. And as you probably know, I'm a huge Tensor fanboy. Read all the manga, seen all of the anime. Japanese sub, obviously. I'm not going to be watching the English dub of Tensor analysis. But I figured I'd talk about what it's covering. If you really don't know what a tensor is, don't worry, you are in good company. In my opinion, it's a topic that is largely skimmed over in undergraduate because, frankly, you can get by without it for a lot of the lower level material. You might encounter things like the inertia or the electromagnetic tensor, but really, you just let the physics guide you to a point where you're like, oh, these all depend on two things. Let me collect all of these things and put it in a matrix, and voila, we have the electromagnetic and inertia tensor. But you don't really talk about what makes a tensor a tensor. A tensor is something that transforms as a tensor, and the first time I heard that, I was like, what? That doesn't help me at all. What do you mean it transforms as itself? What the hell does that mean? It started to make more sense to me when I started to think about vectors, which are just rank 1 tensors. You know, you can have some vector and describe it in some coordinate system, and if you rotate that coordinate system, how do the components of the vector change? Well, they change in a very specific type of way, and that's for any type of vector under that type of transformation. And the pattern, you can go up a rank into a rank 2 tensor or any arbitrary rank and see that you can describe them in a similar way. So if some mathematical object exhibits these specific transformation properties, you call it a tensor. And they're really important because something that my professor likes to use as an example is if you have a bird's nest, say in the corner of your room, and you wanted to describe where it was, you could impose some coordinate system and say, you know, maybe specify its latitude, longitude, and height above sea level to where that bird's nest is. And someone else might use a different coordinate system to impose and get the same answer. And if they really are describing the same thing, there has to be a way to transform from one to the other. So if you know that an object is a tensor, then you already know how those two things will transform into each other, so it can be pretty powerful. I'm gonna put a hat on because I just realized my hair looks like a bent elbow right now. Anyway, since undergraduates are exposed to tensors to varying degrees, when we approached it, we started at the very basics. So needless to say, this homework is a little underwhelming. I can't get into the specific questions because they're written by the professor. They're not just straight out of some book, so I don't really want to give those away. But really, it's really basic stuff. It's making sure people understand covariant versus contravariant tensors. So in one problem, we are given two vectors and a second-rank tensor, and then it rotates the coordinate system and shows what the two vectors transform into. And then from that, we're supposed to deduce what the matrix representation of the second-rank tensor is after that rotation. So that's pretty straightforward. The next one is we're given a 2x2 matrix, and then we're told to prove that this 2x2 matrix is not a tensor. So that's, again, a very straightforward question. You just approach this by showing that it doesn't transform. Its components don't transform as a tensor would. The last question is actually pretty interesting because it's deriving the Laplacian in spherical coordinates using tensor notation. And I say that this is interesting because if you take the partial derivative of some general tensor, the end result in general won't be a tensor. So in order to make sure that it does still describe a tensor, you have to add this correcting term, which are the Christoffel symbols, or in terms of the Christoffel symbols, which I always thought was pretty cool. So, and I'm bringing this up because the Laplacian, if you've had multivariable calculus, is just the divergence of the gradient. So you have to incorporate this idea of what's called a covariant derivative in order to describe the Laplacian correctly. But if you impose the simplifying case that your metric, which describes your space, is just strictly Cartesian, then you can get away with it. Then it actually doesn't matter. But for more general cases, you have to be more careful. So that's probably the one question that I'm kind of looking forward to solving. I don't think I've ever actually derived the Laplacian that way. But that's pretty much my homework. And like I said, it's a little bit underwhelming. There's no differential forms or anything like that. But one thing that is really exciting is I found out, a week or so ago, I went over the classes that I'll probably be taking next semester. And I think I might be able to swap out my computational physics course for a course in graduate general relativity. So that would be pretty exciting. So this is not the end of the road for tensors. But that's it for this video. Hope you guys enjoyed it. Let me know in the comment section if you did. I'm probably going to go die.